So the full form of TBA was network of minima, the Thomson problem. Okay, so I just started this project with David and some computer science people at Notre Dame, and Halim, he's a computational chemist at Durham. So we just have preliminary data so far, but I still think that this project was very appropriate for this particular workshop. So I'm still going to present this. And it's always good to have collaborators in the audience so that I can always put all difficult questions on his shoulder. And so, of course, most of us would know what potential energy landscape is. It doesn't have to be just very chemistry or physics stuff. Potential energy landscape is quite basic in many areas of science. You are given a potential energy function, which is almost always a nonlinear function. Otherwise, we won't be talking about this so extensively. And we have n coordinates, and we want to describe the landscape defined by this multivariate function. And potential energy landscape has, or landscape theory, has found applications in many areas of science and engineering. And I won't even imagine applications of this potential energy function in many areas that I've recently seen. For example, in theoretical particle physics, in string theory, energy landscape is a big sub-area now. Cosmology, statistical physics, condensed matter theory. Probably these things you might have already known, same as chemistry, protein folding and molecular clusters and supercooled liquids and virus modeling and so on. In biology, in mathematical biology, I've seen even the same phrase, potential energy function, in many neural network problems and biomolecules and so on. And recently, I've seen potential energy functions in electrical engineering. So when they model power grids, they also actually talk about energy functions, not in some disguises. They actually talk about potential energy functions. So if you are working on this, all these areas and potential energy landscapes and minimization and so on, you can also apply for NSF funding through these. They have big grants, obviously, so you can also share with electrical engineers. So essentially our goal is to describe the whole multivariate, this multidimensional landscape. But the most interesting points on the surface are minima and transition states. So minima are the solutions of first derivative equations of V, first derivatives with respect to all the coordinates, with constraint that the Hessian has to be positive definite matrix at those points. And transition states are the solutions of first derivative equations with further condition that exactly one eigenvalue of the Hessian matrix should be negative, all other positive. Okay, so these are minima and transition states, and these are the most important points on this surface. So, and we are only going to talk about those in the rest of the talk. And I'll also take a specific potential energy function called the Thomson problem. And the function, the potential energy looks like this. So we have a function summing over all the particles with Coulomb interaction, okay, 1 over Rij, where Rij is the Euclidean distance, but with but this whole function is subject to a constraint, the spherical constraint. It's not A constraint. There are many constraints, so n constraints. Each particle is confined to be on the surface of a sphere. Okay, this is a classic Thomson problem. And our goal is to minimize the energy. So basically, this means that you have to minimize the energy of the electrons interacting with Coulomb interaction, but they have to be confined on the surface of a sphere. Okay, that's what this potential energy function is supposed to do. And this was proposed by Sir J.J. Thomson back in 1904. This was based on his plum pudding model of the atom, which of course turned out to be an obsolete model. So experimental evidences were against this. But still, this particular problem is extremely important, and it has found many applications in many other areas of science, like carbon atoms, so Fullerene patterns of carbon atoms, and colloidal particles, and virus modeling, and so on. And if you are worried about this constraint equations, and then if you are worried that you would then have to deal with this constraint optimization problem, that's not the case here. You can just use a spherical coordinate system so that you get rid of all the spherical constraints, all these constraints. Okay, so your equation, your potential energy function would be just a function of sine and cosine of two angles per particle, and there won't be any other constraint. Okay, so it's an unconstrained optimization problem in the end. So this is this problem is a very interesting optimization problem, and it has found its place in all the benchmark systems for all the novel algorithms for optimization. And the global minimum of this Thomson problem is analytically known for only few number of particles. N is the number of particles, and only for 2 to 6, and n is equal to 12, the exact global minimum is known. And by exact, I mean mathematically provable. Okay. So this is a bit strange because there are some missing n's here, and people keep trying on finding the exact global minimum for all these missing cases, and that's a nice mathematical project for many people. But because these results are analytically known, this can serve as a good benchmark system for many other minimization algorithms. Okay. So this is of course analytical result or mathematical result, but numerically people have tried this and they have found very nice results. David has found I think up to 1,000 particles. Okay? The global minimum for up to 1,000 particles. Before that, all these people worked on numerically finding the global minimum of this model. And recently in 2015, so this year, these three folks also try to work on this again, not only global minimization but local optimization problem of this. Okay. So because I'm working at an applied math department, I'm always asked to put this. I shouldn't write the global minimum. When I talk about numerical algorithms, I can only say that this is the deepest known minimum so far. Okay. So the deepest known minima of this model for up to n is equal to 1,000 has already been found by David and many others. One more interesting thing about this model or this problem is that now we are talking mostly about numerical global minima. For n is equal to 4, 6 and 12, if you plot this global minima, they are basically platonic solids. Okay, so tetrahedron and octahedron and icosahedron. But then they found that for n is equal to 12 and 20. So,
for n equals 8 and 20?
Yeah, sorry, 8 and 20. So, for these two, they didn't turn out to be platonic solids. Okay, so they would be the other two missing platonic solids, and naively we would expect that they would be, of course, platonic solids if 4, 6, and 12 were, but apparently not. So again, we are talking about numerically found global minima here, but that's the current status. So it has been an extremely interesting problem in all areas of physics, chemistry, mathematics. Recently, it has gained even further attention from the mathematicians. So Steve Smale, a Fields medalist, I think he was in Michigan and Chicago, and now he's in Hong Kong. So he came up with 18 problems for the 21st century to mimic the Hilbert's 17 problems for mathematicians. Okay, so in his list of 18 problems, the 7th problem was finding the global minimum of the Thomson problem. Okay, not exactly. So he stated the problem in this way: come up with an algorithm which then construct a collection of starting points at which the potential energy function is close to the global minimum. Okay, he didn't ask us to find the global minimum, but he asked us to construct points so that after that any other numerical minimization algorithm would find the global minimum very quickly. Okay, so essentially, in other words, find or construct a collection of starting points so that the energies of the starting point is of the order log n away from the global minimum. Okay, you have to construct starting point very close to the global minimum, and by very close he meant order of log n, where n is the number of particles. Okay, so this is his 7th problem out of 18, and once there is such a list from such a prominent mathematician out, mathematicians all just jump on working on this problem, and there are lots of papers in mathematics trying to construct these starting points, and he did not say that you should find the global minimum. Yeah?
Can you explain a little bit why the logarithmic potential is the most natural, and in particular, are there other potentials for which this problem is tractable?
Logarithmic potential. This is just distance.
Sorry, I mean the 1 over r potential logarithmic. The 1 over r potential. And is that these are things embedded on a two-dimensional surface, so they have electrostatic forces. I'm just wondering if I said, can you minimize some other potential for points on the sphere? Are there any potentials for which we know how to solve the problem?
Which problem? Finding the exact global minimum.
Is there some other repulsive force for which we know how to do that?
Probably not.
The generalized Thomson problem for lots of different powers about. And I think the analytical solutions are probably all the same, actually. Because of symmetry.
I know Henry Cohen at Microsoft used to work in this, like finding different forms of the
So in some sense, all powers of R are, from a
Yes,
mathematical
yes, yes.
point of view, equally worthy of study.
Yes,
It's not just this one over R.
that's true. Yeah. This is the problem that Smale proposed. He just wrote this problem down in this particular form instead of finding the global minimum directly, because then you can also use the starting points to solve a system of random polynomials. Okay, it's one of those mathematical thing. One thing is related to another area of mathematics via duality. Okay, so once you construct starting points of this problem, of the Thomson problem, then you can use the same starting points to solve a system of random polynomials.
So that's where the log n. If it's within log n, then it's related to this polynomial problem.
Yes, yes, yes. This was a very interesting problem and a very interesting solution that these three folks came up with: Armentano, Carlos Beltran, and Michael Schub. Michael Schub was, I believe, a student of Smale, now at City College, New York. So they said that you take a random univariate polynomial. Okay, so univariate polynomial of degree n, but all the coefficients are chosen from some Gaussian distribution. You solve that univariate equation. There are always n roots, obviously, so you get n points. Then you stereographically project it so that you get two coordinates for each root. Okay, and that combination of points will be a good starting point for this problem.
This is because the roots of random polynomials have an electrostatic repulsion, just like the eigenvalues of random numbers.
Yeah. So that was a very interesting solution as well. You just solve a random univariate polynomial. And the roots of this apparently through this list, the seventh problem, are related to starting points of multivariate polynomial equations, and then those starting points are also related to this Thomson problem. Okay, so everything is so nicely woven here. That was a very nice solution. We picked up this problem from a different point of view, using all the machineries that David and his group has developed. So again, so we use this very nice Gmin and Optim softwares that David has written. It has many algorithms implemented which find many minima, the global minimum, so numerically the global minimum. It also finds transition states, and it also finds connections among minima and transition states. Okay, so we use these sophisticated tools, again just numerical, of course, so I don't have any proof for whatever I'm going to talk about from this point.
You should probably say that 135 is definitely not convergent.
Yeah, yes. So that's why I said in the beginning that I just have preliminary results.
Both points will go.
Yes. So now I'm finding minima of the Thomson problem numerically, okay, and also transition states numerically. So these are our preliminary results. Here on the x-axis we have the number of particles, 135, 138, 41, and so on, just in the multiples of 3. And these were two old estimates on the number of minima. This is not actually an old one. This is 2015, just this year. But our results suggest that we have many more minima for this problem. So because this is a log scale on the y-axis, the number of minima grows exponentially, but it's still slow exponential compared to many other models like Lennard-Jones or and so on. Okay. Here we have transition states. The transition states are far more than the number of minima as expected. So these are our results. Of course, these are not the main point of this talk, but we have a further result, and which was mainly inspired by a paper by Jonathan Doe in 2002, and he constructed the network of minima in the following way. So each minimum is connected to another minimum via a transition state. Okay, so that.
What do you mean by transition state?
Transition state is a saddle of index 1. So a stationary point of the potential energy landscape that has exactly one negative eigenvalue of the Hessian. Okay. So it basically mediates one minimum to another. So that's why it's called transition state. So each minimum is connected to another minimum via a transition state, and it goes back to Stillinger and Weber. And David probably is going to talk about many methods to find all these connections and transition states and minima. But basically, this is all we need to construct a network. Okay. So from this multidimensional landscape, we have now gone to an undirected, unweighted network of minima, where the minima are now our nodes and transition states are now our edges. Okay, so if one minimum is connected to another, then there is a line between them. If they are not directly connected, then there is no line. Okay, so now we have a very natural network structure here. Again, these are unweighted and undirected. So for n is equal to 144, we have almost 5,000 minima and some 100,000 connections. So it looks horrible. Of course, there is no information we can extract from this kind of things.
Excuse me, but in that previous slide, there were some exceptional points. Are they special somehow? Are they like really global? No, next slide. Yeah, there's a point way off in the southeast there that's off. What is that? And then also in the southwest, there's some weird.
No, I think the global minimum is somewhere here, which is not visible properly. But I don't think that there is any specific property here. It's just a bit.
That one hasn't been searched very well yet.
Yeah. It's not a loop. I checked this. There are 2 points here. It's a way Mathematica plots this. Okay.
Did you look at the permutational degeneracy?
We have removed that.
Yes.
So they are unique minima, unique transition states, and okay. So of course that plot doesn't give you much information. So we started computing all the basic properties of networks. So for example, here we are computing the average shortest path between all pairs of minima. Okay. So here I am plotting number of nodes or number of minima on the x-axis. Here we have average shortest path, and this is 2.5 to 3. Okay, so each minimum can be reached by any other minimum via just 2 or 3 hops. Okay, even though we have this 5,000 minima or 10,000 minima here. So on an average, there are 2 to 3 hops between any pair of minima. And the diameter is also 6, 5, or 6. Okay, diameter is the longest, shortest path. So now back to Smale's problem. Smale's problem was to construct a starting point that is log of n away from the global minimum. Okay. Our results suggest that any minimum is only log of number of minima hops away from the global minimum. Or it is the global minimum is never too far from any other local minimum. Yeah?
So it would be really nice to see a movie of a path from one minimum to another that goes to the saddle point so one can get a sense of what type of rearrangement that path corresponds to.
Wait till 11
The fact
o'clock.
that the diameter is so small suggests that these are not really local rearrangements.
They're highly cooperative in general. It's a very long range potential. I have a movie or two.
So this is our result. Here I should emphasize that I'm talking about hops and not the actual Euclidean distance. Okay, any minimum. So if you have a very bad numerical algorithm, it gives you a very bad local minimum, very high-lying minimum. You are still not far away from the global minimum, just 2 or 3 hops away. Okay.
But the barriers could be high.
Yes, so that's why I emphasize that I'm not putting any direction or weight. So I have no information about barrier height here, and that's going to be our next step in the project. Okay, but for now.
You do have all the information. You just
Yes. So that is a characteristic of a small world network. Okay, and to confirm that we indeed have a small world network, we computed the usual clustering coefficient and compared it with the clustering coefficient of a random graph of the same number of nodes and edges. Okay, and whenever the ratio is much higher than 1, then it's also a strong signal that we have a small world network here. So then we plotted a node degree. So node degree is the number of connections that each node has. Okay, and the cumulative distribution of this. And we have power law kind of thing. Okay, so of course I cannot always claim just by looking at these kind of plots that I have a power law graph. I have to do the statistical analysis that Newman et al. Proposed. So our statistical hypothesis that this data fits power law is still valid. Okay, we haven't found any counterexample statistically speaking. So on the basis of that result, that statistical analysis, I'm saying that this is a power law. So these data are just power law.
What's the index of power law?
2.1. So it's right in the 2 to 3 range. Okay. So again, this is this network of minima is not only a small world network, but it's a scale-free network. Okay. Then we plotted potential energy minimum. So the value of the potential function at each minimum on the x-axis, and on the y-axis we have node degree of that particular minimum. Okay. So take each node of the network, compute the potential energy function corresponding to that node, and also compute the node degree of that node and plot that. Okay, so this is our scattered plot. This is the beamed average. Okay, the red line. So this is log scale. This is just linear. This point corresponds to the global minimum, okay, the lowest energy. And then we have many local minima here. So this plot is very interesting because it says that the global minimum is most connected, okay, and local minima, high-lying local minima, are the least connected nodes here. So in short, you are given a very complicated multi-dimensional surface energy landscape, but the global minimum is most connected. So if you have an algorithm which just follows this connection, then you can quite efficiently climb this and reach the global minimum. Okay.
More interesting, do you have some very local minimum there that have almost the same energy?
Yes. No.
Just go down to where
Here?
you have this point there. Just
They are different. They are different points here.
so, but that would be a local minimum that is almost the same energy, but it's not connected to anybody else, right?
Yeah. So that's an interesting result, but more interestingly, this is a static network. Okay, once you fix the number of nodes, number of particles for the Thomson problem, it's static. We are talking about potential energy, so there is no dynamics here, and number of minima would be just there. You just need to find them. Number of transition states also would be there. Normally, you have power law or scale-free graphs if you have preferential attachment. Okay, so you started with one network, and then more new computers came in, and then they started attaching with each other with some preference, and then you have a scale-free network in the end. Here, there is no such evolution in time. Of course, this is not an exception to this phenomenon. Our network is not an exception. There are one or two other networks coming from biology, I know, which are also static but also show this scale-free nature. Okay. So these are our results, and the next step would be obviously putting weight and direction. So by weight, I might mean barrier height, for example, and direction, and so on. So can we utilize this feature of scale-free or small world network characteristic to construct an algorithm to find the global minimum? Can we follow these connection paths somehow and find the global minimum very efficiently? We don't have a nice answer. Of course, Gmin and Optim implicitly uses some of these features of a small world network, but we are also trying some homotopy continuation-based algorithms to follow these paths.
So I'm sorry, you said you're using some result from 2002 that says, given the number of particles, you can produce all of them, including the global, right?
No, I just said that I used the same strategy that Jonathan Doe in 2002 followed. He used it for the Lennard-Jones potential. I am following the same strategy for the Thomson problem, but with more information.
But the point is you have an algorithm that can spit out all of the minimum.
No.
Right now, that's where you're getting these
No.
No.
I only
You get all those minimum from the
Gmin and Optim, which are softwares which implement many sophisticated algorithms to find numerically many minima and many transition states. I cannot guarantee that I have all minima or all transitions. So I said I cannot prove anything after a certain point. All I have is numerical data. Okay. No proof of this. The second question is the small world or nature of network of minima universal? Say you have some other kind of potential. Would you expect the same feature? I don't know. So we have data from Lennard-Jones potential from 2002 paper of John Doe. We now have data from Morse clusters analysis, and they also suggested we certainly have this feature. We don't have any data so far. But of course, a network of minima of some potential being complete network would be too trivial. Each minimum is connected to every other minimum. That's most probably not going to happen. Okay, but is there any other kind of network? We don't know, but classifying all these would be quite interesting. And why this property? It's not a philosophical why, it's a mathematical or theoretical why. Why should we expect this kind of property? And what other network topologies could we even imagine to have for some other potentials? Okay? And can we classify potentials, different potentials, based on the properties of the network of minima? Okay. How about network of minima of the free energy landscape? We don't know yet. We haven't started it yet, but hopefully we'll do. And network of minima for potentials on networks. So people talk about XY model, for example, Ising model, Heisenberg model, free network, or all sorts of other networks. You find minima and transition states of those models. What is the network of minima look like? Is there any correspondence between them? And okay, I had to squeeze this. So networks of higher index saddles. What happens for networks of high index saddles? And we had actually written a paper 3 years ago. David and summer student back in Cambridge. We had started from a maximum and then followed just this paths we didn't call network back then, and then we eventually always found the local minimum following all higher saddle index paths, and that worked very well. But we didn't know about these results back then, and we might want to revisit them. So I'm now concluding. So of course, potential energy landscape is an exciting area of research, but now with with new results, we are combining all these kind of things: chemistry and physics, obviously, network science, and optimization and complexity, and these random univariate polynomials and random multivariate polynomials. Okay, so I'll stop here. Thanks.
First one is that, like, if you were doing the same Thomson problem on the surface of a circle, it's trivial, and on the surface of a sphere in 3 dimensions, it's like obviously not a trivial problem. What about the dependence on dimensionality? Is there some other higher dimension of the problem comes simpler again?
So of course there are all sorts of generalization of the problem, but 3 dimension is natural for chemistry applications. So we. I'm pseudo-mathematician, pseudo-chemist.
And the other thing is that I've actually, while you're doing your talk, I was searching on the archive, because I remember a paper, I think it was by Michael Moore or something like that, where they actually visualized like the positions of the particles in the minimum. And there's like beautiful patterns of disclinations and dislocations. Do you have anything to say about the geometrical arrangement around the minimum?
And not yet.
I'll just put that slide back in.
So wait for his talk then. Okay.
Actually, Mark White and David Nelson also, they look at the distribution, generalized Thomson problem.
That's okay, that's what I.
Gamma between 0 and 2, not only
Yeah. I mean,
interaction with different exponents, and they found very fine binary.
yeah. So David and Halim, my other collaborator, have been working on this generalized Thomson problem.
That this could probably explain or go in the direction of explaining why they follow a law. If they have something that's truly symmetric, there are probably many ways of creating this explanation. There's something that's very asymmetric, just as string or so. There are not so many ways of creating local minimum close to that. Something along those lines.
Good question.
Yeah, I have a question concerning the numerical method that you used to find minima. I would assume this is some kind of simulated annealing.
Oh,
Is that correct? Or?
No.
No, okay. Because my question was, when you look at this network, this path going from the low degree to high degree to low total minimum, does that, am I interpreting this right? It basically means if I would take those paths because they're unweighted randomly, that I would most likely end up in the global minimum?
Yes, but then because this is unweighted,
Because it's unweighted.
yeah, then probably yes. But in practice, it is not unweighted.
Thomson problem itself, or is this something that comes from like the way that you're finding?
No. No.
I think it comes from the landscape. And one of the questions is this small world property generic to potentials. I don't think it's generic to potentials, I think it's generic to particular systems. Remember that the landscape can change completely with size for the same potential. And I think the small world property is one that we're going to find whenever we have a palm tree type landscape, where there's a well-defined global minimum at the bottom with no competition from other low-lying limits separated by large barriers, which I would call frustration. So when you have that form of landscape, you get efficient self-organization into the ground state. Those are good structure symbols. And I think they will all exhibit small world properties. I can't prove that. But I think for every one we've seen, it is true. They can be.
Yes.
So another attractive set of points on the sphere is an approximate spherical design or approximate quadrature rule, which creates a small average for all spherical harmonics up to a certain order. I'm sure people have explored this, but is there any known relationship between these two problems? Are Thomson states good approximate quadrature rules, or vice versa?
I think you have explored that.
Uses the Thomson problem solutions to see his quadratures when he does simple exponential theory.
So is there anything rigorous known about...
No, they just work that stuff.
Yeah.
And he hasn't, and they're available on the web, so it's down there to use them. I'm not claiming they're optimal at all.
Can you, so probably we need the barrier heights, the directness and the weightiness, but can you say anything about phase transitions? How does that work? So whether you have a deep global minimum, see what phase transitions you do. So I'm thinking high entropy, high energy, low energy.
Not yet. Probably that's also one of the reasons why I should also consider free energy minima network.
One more question. So you mentioned the free energy landscape, but I'm not sure how you define that here. I mean, are there, I mean, I can imagine that if you had a notion of macro state, for instance, things with a fair amount of crystalline order, then you could define a free energy landscape. But in the absence of that, I'm not sure what you mean about identifying minima saddles and barriers in the free energy landscape.
Yeah, you mean for this particular model?
Yeah.
I didn't mean for this particular model. Just in general, I should explore network of minima of free energy.
Okay. Well, for this one, I guess you
Well, the simplest way to do it is to do per minimum and use the harmonic vibrational density space. And you immediately get green disconnectivity graph that way. And you can use a recursive lumping scheme based upon barrier heights, free energy barrier heights. Choose a threshold and a temperature, and you can log your states recursively, self-consistently that way, and simplify the graph.
So it's assuming harmonic.
Well, no, and that's just a convenient measure.
Okay.
You could use the right entropy if you could be bothered to calculate it. The algorithm would function the same way.
Okay. So it's time for coffee break now. Thank you.
Thanks.